Good afternoon, my dear student. Hope all of you are very fine. Today we will discuss about the application of Laplace transformation in analyzing of networks. Okay. So far we have discussed about the properties of Laplace transform and also the concept of singularity function. Now we will try to understand the response of a circuit in presence of different types of singularity function. For example, impulse function or delta function or unit step function or ramp function. Okay, you have a good concept about this function, delta function or impulse function, unit step function, and also ramp function. These functions are known as singularity function because we can compute or form a new signal by using this signal, or a signal can be represented in terms of this function. Before going to discuss about the impulse response or step response of a RL circuit, let me tell you the Laplace transform of a periodic function. Okay, here you just see the present slide. In this slide I have given a RL circuit, whatever we have discussed in previous class. Okay, that time we have calculated the transient response as well as steady state response of a RL circuit for a excitation DC excitation V. Okay, supply voltage V. Now you see that I have crossed out the DC supply voltage V. Instead of this voltage, I have provided a step input or step excitation V naught U of t. You know that U of t is nothing but a step function. This function has a non-zero value, that means equal to 1 for t greater than equal to 0 in this range. If t less than 0, then this function will become 0. Okay, and the strength of this function is V naught. You know that the value of value of unit step function is 1, but I have given V naught as strength. That means for this case V naught, the function will be equal to V naught for t greater than equal to 0. Okay, now your task is to calculate the output of this circuit. You know the response is nothing but the output of a circuit or network. So for this case, the input is a step input or step function. That's why its corresponding output is known as step response of this circuit. This circuit is a very simple circuit, that is a series RL circuit, and you know the differential equation for this circuit. If you consider the switch is closed at t equal to 0, okay, the switch is closed at t equal to 0. Let me write here. Let us consider, or we assume that the circuit, the switch associated with this circuit, the switch is closed at t equal to 0. Okay, at t equal to 0 the switch is closed, and the input, you see the input is x of t, which is nothing but v naught u of t. U of t is the unit, this is the step function, unit step function. Okay, now you can write the differential equation for this circuit. Suppose you consider I current is flowing through this circuit after t equal to 0. So we can write the differential equation for this circuit. You write the differential equation for this circuit is, for this circuit is I current actually flowing through this circuit. We can write using Kirchhoff voltage law, R I of t plus L di of t by dt equal to the supply voltage V naught U of t. Everyone, first write the differential equation for this circuit using Kirchhoff voltage law. Using Kirchhoff voltage law. This is equation 1. Equation 1. Okay. You consider I current after closing the switch, I current flowing this circuit. I current flowing this circuit. I of t. Okay. After closing this switch. After closing this switch. After closing this switch. Okay. So now you got the differential equation for this circuit. Our objective is to calculate the response of this circuit, I mean output of this circuit, I of t, output of this circuit. So you would know the Laplace transform of derivative of a function. Now you take Laplace transform of equation 1. Now let me write this statement. Taking the Laplace transform on both sides of equation 1. Taking Laplace transform on both sides of, or for equation 1. For equation 1. Okay. Taking Laplace transform on both sides for equation 1. This is equation 1. So Laplace transform, you write Laplace transform of the equation 1. We can write R. Suppose the Laplace transform I of t, the current function, is capital I of S. You know S is the Laplace transform. In frequency domain we have actually used this notation I of S. And now you tell me the Laplace transform of L di dt. You know L is a constant, you take outside of this bracket. So, and now you tell me what will be the Laplace transform of the derivative di dt. The derivative di dt, you know that Laplace transform of the derivative of a function is s into Laplace transform of the function minus the initial value of the function. We have obtained or derived the Laplace transform of the derivative of a function in previous class. Okay, so you use that concept. Now I can write I of s is I of s minus the initial value of the current function I of 0. 0 plus, for this case, at t equal to 0. Okay, and this will be the capital V, not small v, equal to, you can write v naught is a constant term, v naught, and the Laplace transform of unit step function is nothing but 1 by s. You know it. If you take Laplace transform of a function, so you just write v naught by s. If you have is I naught, yes or Kodif, you are right. Okay. Uh, so now you write the Laplace transform of equation 1. The advantage of Laplace transform is that without any rigorous calculation or without considering the initial or boundary condition of the network, we can calculate it in response. So far, we have calculated steady state response as well as transient response of RL circuit, RC circuit, mean first order or second order RLC circuit in time domain. But in this case, we have considered frequency domain concept by using Laplace transform because it helps us to calculate the response of a circuit easily without any rigorous calculation. Okay, so therefore we obtain the Laplace transform of this equation. Now we can write I of s, I is the Laplace transform of the current I of t, equal to, we can write v naught, okay, divided by you just take common is into r plus l s. Okay, everyone write the I of s in terms of remaining factors. V naught divided by s into r plus ls. What is the value of I of I naught? Since I naught equal to 0. Since I naught equal to 0, because initially the inductor is actually fully charged. I mean the voltage drop across inductor is the supply voltage. It will act as an open circuit, therefore current will be 0. At t equal to 0, the current through this inductor is equal to 0, because you know that inductor act as an open circuit element at t equal to 0, because you know that V equal to VL, the voltage drop across inductor is equal to the product of inductance value into the rate of change of current, VL equal to L di dt. If t equal to 0, that means VL is infinite. That means it acts as an open circuit element. Therefore, the corresponding current becomes 0. Okay. Now you can write this thing. You simplify this thing. You use partial fraction expansion concept. Okay. partial fraction expansion concept. That means the ratio you can express in terms of partial fraction component. I mean, so here we can write this equal to V naught divided by L into, you just take inside a bracket, it's good, V naught by L. Everyone solve it yourself and compare your result with my result. Okay, then you can write, let me write it, L by R into, you can write 1 by S minus 1 by S plus R by L. Everyone look at the expression L by R by L. Okay. Therefore, I can write this thing finally V naught divided by capital R into 1 by S minus 1 by S plus R by L. Okay. Any doubt regarding the, okay, this is equation 1 by S plus RL. This is equation 2. You write equation 2. Okay. V naught by R 1 by S divided minus 1 by S plus R by L. Everyone try to understand this concept, because in any competitive exam, not only for your degree course exam, in any competitive exam, you will face such problem, and therefore you need to use Laplace transform concept to solve those problems instead of time domain analysis, because time domain analysis takes lot of time. So therefore we will prefer that approach which takes less time and help us the problem more easily. So therefore we will use Laplace transform to solve network theory problem, especially for AC analysis and also for DC analysis. Okay, especially for AC analysis you must use the Laplace transform concept to solve network analysis problem. So write first you write the differential equation of the circuit by using Kirchhoff voltage law. After that, you take Laplace transform of the differential equation and you arrange the differential equation in terms of current. I mean, you arrange the differential equation in the form of current component. Okay, so you take current component at the left hand side and you take other remaining component at the right hand side of the equation. So therefore we have obtained I of S, the Laplace transform of current, equal to V naught by R. Finally V naught by R into 1 by S minus 1 by S plus R by L. Okay, R by L you take within bracket, otherwise it is confusing. So this is the final expression. This is the final expression of I of S. Let me write here I of the Laplace transform of current component. Now our objective is to calculate the response step response of this circuit. And you know that response means time domain representation of the current component. So you just take inverse Fourier transform of the equation 2. Taking inverse Fourier transform, inverse Laplace transform, Laplace transform Laplace transform of equation 2, we will get I of t. The inverse Laplace transform of I of s is I of t. V naught is our constant term. It will be same. V naught by R. You take within a bracket this factor. Okay. And this will give you 1 by R is equal to, you will get unit step function u of t minus what you will get, the inverse Laplace transform. You know that e to the power minus at Laplace transform is 1 by s plus a. Therefore you can write e to the power minus a, for this case r by l. A here is r by l into t. Okay, you just remember the inverse Laplace transform of an exponential terms e to the power minus at. Okay, any doubt? So finally you can write I of t equal to this term. Instead of ut we can write 1. This and this you can write 1. This is unit step function. Any doubt? Any how do you derive the final expression? Please repeat. Final expression. Actually, I have Shubham Saivaraj. First, I have considered the differential equation for the given circuit. The given circuit is a series RL circuit, and the input is an unit step input. Its strength is V naught. V naught u of t. I have written here, you see that input is x of t equal to V naught u of t. We assume the switch is closed at t equal to 0. So therefore the differential equation for this circuit is R I of t. The voltage drop across resistance R is R I of t. The voltage drop across L is L di dt. This will be equal to the supply voltage V naught U of t. Okay. Any doubt regarding the equation 1? Saiva, you just try to understand what I am telling you. First, you write the differential equation of the given circuit. Given circuit is nothing but a series RL circuit. So you can write the supply voltage is equal to the algebraic sum of voltage drop across individual component associated with the given circuit. So for this circuit there are two components, resistance and inductance. Therefore the supply voltage V naught U of t is equal to the voltage drop, the sum of voltage drop across R, that is R I of t, plus the voltage drop across L di dt. Okay, equation 1. Now you take Laplace transform of equation 1. Laplace transform of equation 1. So here we have considered the Laplace transform of I of t. This function is I of s. Let me write here. It's good. The Laplace transform of the current function I of t is I of s. Okay, I of s. Laplace transform of the current I of t is I of s. Taking Laplace transform of both sides of equation, so you can write r is a constant term. R will be same as in equation 1. I of t Laplace transform I of s. L is a constant term, same as in equation 1. And di dt, you know the Laplace transform of the derivative of a function is s I into s the frequency domain component is into Laplace transform of the function minus its initial value. You just remember. And this function v naught u of t, v naught is a constant term, so v naught, and u of t is Laplace transform u of 1 by s. Let me write here inside a bracket the Laplace transform of u of t unit step function is 1 by complex frequency s. S is a complex frequency. Now we can write I of s equal to v naught divided by s into r plus ls. You just simplify it, and I naught is nothing but equal to 0, because you know that inductance act as an open circuit element at t equal to 0. Therefore, the current through it's equal to 0. And finally, you take inverse Laplace transform of equation 2, because our objective is to calculate the response, I mean time domain expression of current for the RL circuit. So therefore, the I of t equal to v naught by r 1 minus e to the power r t by L. This is same. Okay, we can calculate this thing by using time domain concept. We have derived these things in previous classes. Okay, and you know that I of t has two terms. One is steady state, another one is transient. And you see that v naught by r is nothing but a steady state response. On the other hand, v naught by r into e to the power minus r by lt is a transient response. So therefore, total response of this circuit is consist of transient as well as steady state response. And the time constant of this circuit is L by R. The time constant of this circuit is L by R. Now, everyone calculate the impulse response of the circuit. Okay, impulse response of the circuit. We have just derived the step response of a RL circuit. Now you calculate the impulse response for the given circuit. Step response means your input is a step function. Impulse response means your input is a impulse function or delta function, delta of t. So I suggest all of you to calculate the response, I mean I of t, for the same RL circuit in presence of an excitation or input impulse response. Now Saiba and other everyone calculate the impulse response for the same circuit. Impulse response for the same circuit. This is the your answer. This is the actually step response of your circuit. You write it. This is step response of your circuit. Step response of the given circuit. And you know that, you see that this circuit, the response has two parts, transient as well as steady state given circuit. The transient part is, let me write it in separate, v naught by r minus v naught by r, you v naught by r you take within a bracket into e to the power minus r t by L. Okay, and this is, you make it as a subscript, subscript, and also v naught, and this is as a superscript notation. Okay, and this part is the steady state response. Steady state response. Everyone calculate the impulse response for the same circuit. You consider delta function as the input of the given circuit plus transient response. Okay, now you calculate the impulse response for the given circuit. You consider input is a delta function. Calculate the impulse response for the given RL circuit. Okay, for this case, input you consider x of t is nothing but an impulse function or delta function, delta of t. Everyone solve it yourself and write your answer. Okay, now input is delta of t, that means delta of t impulse response or delta function is equal to 1 for t equal to 0. You know it. Now you calculate it yourself because I have already derived the step response for the RL circuit. Now you calculate impulse response. That means input is a impulse function or delta function, and you have a good concept about step function, impulse function, ramp function. These functions are nothing but singularity function. We have discussed in detail about this function. So you just use your concept here and solve the problem. The first, you know that first step is to derive the differential equation of the given circuit. So same, you just write the differential equation for this circuit equal to, you write it L di, current is t, dt, current I of t a plus r I of t equal to delta function. Your input is a delta function. You write delta of t. Everyone first write the first order differential equation for the given circuit by applying KVL. Okay, we can write L di dt plus Rit equal to, now you consider this is equation 1 and you take the Laplace transform of this equation. Taking Laplace transform on both side for equation 1. So what you can write? You can write L into S I of S minus the initial value of the current I at t equal to 0. Then you can write plus R I of S, the Laplace transform of the current function, equal to, you tell me what is the Laplace transform of a delta function. So 1 by L to the power of, okay, I of t equal to 1 by L e to the power minus R by L t. Okay, correct. But you just replace this L. This will be I of t. Nivedita Bhagat, This will be I of t instead of L of t. L of t, this will be I of t. You just correct this. Your answer is correct. Now, you tell me what is the Laplace transform of an impulse function? Of an impulse function. Laplace transform of an impulse function. Impulse function. Anyone tell me what is the Laplace transform of an impulse function or delta function? I have derived the Laplace transform of an impulse function or a delta function in previous class. The Laplace transform of delta function is equal to 1. Now you write Laplace transform 1. The Laplace transform of a delta function is equal to 1. Now you simplify this thing. You write in terms of current. So I of S you can write, and you know that this value equal to 0, I of t equal to 0. So you just make it equal to 0. So finally you can write I of S equal to 1 divided by R plus 1 divided by R plus L into S. So this thing you can simplify it as a partial fraction expansion from you can write 1 by capital L. You consider within a bracket 1 by L 1 by L into you can write this within a bracket 1 by S plus R by L R by L R by L. Okay. So now you take this, suppose this is equation 2. Equation 2. Here you write the Laplace transform of delta function, since Laplace transform of delta function is 1. Okay, delta function is 1. Delta function is 1. So therefore we got the current expression in frequency domain. Now we will take its inverse Laplace transform. Taking inverse Laplace transform, because our objective is to calculate the response in time domain, inverse Laplace transform of equation 2. So we can write I of t equal to 1 by capital L. You take within a bracket this term, otherwise it will create confusion. So you just write, you can write e to the power minus R by LT, R by capital L T. Okay, this thing. And you can write u of t here, but u of t is 1, no problem. This expression is correct. Okay. So therefore, the impulse response for a series RL circuit is I of t equal to 1 by L e to the power minus R by LT. Let me write here. You just remember this thing. The Laplace if a function f of t equal to f of t is equal to e to the power minus at. Let me write here, f of t is a function and this function is e to the power at, then its Laplace transform f of s equal to 1 by s plus a, sorry, 1 by s plus a. If a function given by f of t equal to e to the power minus at exponential term, then its Laplace transform is 1 by s plus a. So if Laplace transform is 1 by s plus a, then its time domain e to the power minus at. So for this case, equation 2 you see, a, for this case a is equal to r by l. So therefore its inverse Laplace transform is e to the power minus r by l t. Okay, you just remember this part. Laplace transform of an exponential function is 1 by s plus a. Therefore, the inverse Laplace transform of f of s is e to the power minus at. Okay. If anyone has any confusion or doubt regarding the step response or impulse response of a series RL circuit, you write your confusion in the chat box. Okay. Therefore, we can compute the response of a given circuit by using the concept of Laplace transform. Whatever the circuit, RL, RC, RLC, RLC circuit, whatever, we can compute. And you remember that the response for a unit step input function is known as step response, and the response or output of a circuit for impulse input or impulse excitation or delta function is known as impulse response of the circuit. Impulse response of the circuit. Okay. One thing, you can calculate impulse response from the step response without calculating the without considering the differential equation Laplace transform the steps. Okay, for impulse function, you know that impulse function can be represented in terms of unit step function, or unit step function can be represented in terms of unit step function. They are related by integration or differential operation. If you take differentiation or derivative of a unit step function, then you will get impulse function. If you take integration of an impulse function, then you will get unit step function. So if you got any function in any question comes such type of problem that you calculate impulse response, step response is provided, you just take derivative of the step response. Whatever you will get, that will be the impulse response. Okay, whatever the step response you obtain, you just take derivative of that response, you will get impulse response. You will get impulse response. Okay, without further calculation for impulse input. If you got step response, you just take derivative of the step response. It will give you the impulse response, and vice versa. Okay, now you calculate the step response for a RLC circuit. Everyone do it yourself. Everyone compute the step response for a RLC circuit. You can compute the step response, impulse response for a RC circuit in the same approach, but you compute the step response for a second order circuit, RLC circuit. Calculate the step response for a second order circuit network. I mean, so this is a second order network. Now you consider this input. The input is, you just consider unit step input. You cancel this input. This is a DC input, and the unit step itself a DC input, but you consider DC circuit. Okay, and here you write input is x of t is x of t equal to v naught u of t. V naught u of t. V naught is the string. You can consider u naught, u of t only, no problem. But v naught here I have given. Okay, you just make it small from. This is your input, x of t equal to v naught u of t. This is the unit step input. You calculate the step response I of t for this circuit. What will be the expression of I of t using Laplace transform? Okay, using Laplace transform. You know that the graph for a step function, unit step function like this. If we consider this is t, this portion is t, this is t, and this portion is u of t, this is u of t, then you know that it will be equal to 1. Then you know that this will be equal to 1 for t equal to 0 or greater than 0. This you know. But for this case, I have given v naught. V naught. You see, this is v naught. That means this is multiplied with a constant term v naught. Okay. This function is multiplied by a constant term. Constant term v naught. So we can write this will be equal to v naught. Instead of 1, this will be v naught. Okay, any doubt? The input for this circuit is look like this. V naught. Okay, now you calculate the step response for this second order circuit. Second order means the order of the differential equation is 2. d square term will come. Okay, dt square. So now first you write the KVL, Kirchhoff voltage law equation. You apply KVL and you write the differential equation for this circuit. So you know the differential equation is L di dt plus R I t plus 1 by c integration 0 to t I dt equal to v naught u of t. V naught u of t. So everyone first write the KVL differential equation for this circuit. Let me write here and you compare. You consider the switch is closed at t equal to 0. The switch is closed as t equal to 0. We can write L di t by dt dit by dt plus Ri of t plus the voltage drop across this component. Voltage drop across R is Ri. T voltage drop across L is L di dt. Voltage drop across C, Vc is what? 1 by C integration of 0 to t I of t dt. Okay? 0 to t, you just take I of t dt. This equation you consider, this is equation 1. Equation 1. Now everyone take the Laplace transform of the equation of the equation 1. I mean, you take Laplace transform of equation 1. In this case, you must use the Laplace transform of integration of a function. In last problem, we have used the concept of Laplace transform for the derivative of a function, but in this case we need to use concept for Laplace transform of derivative as well as integration. This is the only difference. Otherwise the approach will be same as previous case. Okay, so everyone take the Laplace transform of equation 1. Okay, I have made a mistake here. You just write this will be equal to the supply voltage. What is your supply voltage? V naught U of t. Okay, you know the algebraic sum of the voltage drop across individual component is equal to the supply voltage. So you just equation 1 and then you take Laplace transform. Taking Laplace transform, everyone do it yourself and tell me your answer. Laplace transform on both sides of equation 1 Okay, now you write yourself. So you know L di dt, L I of s, initial value is 0, R I of s, and 1 by C I of t dt equal to, you tell me. This will be I of s by s. The initial value, let me write it L s I of s, and initial value is 0. No need to write it again. Plus R I of s, the Laplace transform of current component, plus this will be equal to I of integration is by C of s equal to V naught divided by s. Okay, V naught divided by s. Now you will write it. You will rearrange this equation in terms of current component. You express current component in terms of others. This is equation 2. So you just rearrange this equation. You write Is on the left hand side of equation 2 and write remaining terms on the right hand side of the equation 2. So we can write I of s everyone solve it yourself. I of s equal to, you can write finally V naught divided by L a square plus r is plus 1y capital C. Let me write it in proper form. L a square. Okay, r is plus 1 by c. This is. Now you take inverse Laplace transform of this equation, and you will get the final result. You will get the final expression I of t equal to v naught by L. Okay, so you can express this equation as a partial fraction expression, and then you take inverse Laplace transform. One thing, you remember that to solve the equation in frequency domain, or if you want to take the time domain value from the frequency domain expression, you need to express the frequency domain expression in the form of partial fraction expansion. That will help you to easily take Laplace transform, inverse Laplace transform of individual function. Okay, suppose this function you see I of a is equal to v naught divided by L s square plus r s plus 1 by c. This is a complex. We don't know the inverse Laplace transform such type of function. Numerator v naught and denominator L s square plus r s plus 1 by s. Here you see that the roots of this equation, denominator part, repeated a square. In last problem we have seen that there is only one factor is. Okay, so to solve this thing, first you expand it in partial fraction expansion, and then you take inverse Laplace transform. Otherwise it is difficult for us to calculate inverse Laplace transform of this function. So let me write this thing, then you can easily understand how do you express a function in terms of partial expansion form. So we got this. So I can write I of is equal to v naught divided by L into s minus p1. Okay, and s minus p2, where p1 and p2 are the roots of the equation, minus p2. Okay, if you have any confusion to understand this part, you write in your chat box. We actually express this thing as v naught L s minus p1 s minus p2, where p1 and p2 are the roots of the equation, denominator. Actually your denominator part is equal to you have L square plus r is plus 1 by capital C. That is the quadratic equation. So you know that for a quadratic equation has two root. Quadratic equation. So this equation has two root is P1 is P2. We have considered here. Okay, S1, S2, whatever. P1, P2. So therefore we can write this thing like this: S minus P1, S minus P2. And you know P1, P2, you can calculate the value of P1, P2 by using the standard formula, minus v plus minus root over b square minus 4ac by 2a. By using that expression you can calculate P1 and P2, and you just put this expression in original I of s equation and take inverse Laplace transform. So the roots, let me write here, the roots of the quadratic equation, take the roots of the denominator, you write denominator r r r p1 and p2, say. Okay, say. So you can calculate p1 and p2. P1 p2 equal to minus b plus minus. You just use that concept, standard formula derived by Siddhar Acharya. So you just write uh, plus minus root over b square minus 4ac by 2a, root over b square minus 4ac by, you take these things, 4ac by 2a. So you will get the value of this, and this will be in terms of L R C. Here b, these things, ax square bx plus c, you just consider s square plus ry l is 1y lc. Okay, so you can calculate this thing. P1 P2 will be minus r by 2l plus minus 1 by 2l root over r square minus 4l by c. So you will get final expression of the current component I of t. You will get the final expression of the current component. So let me write here the final expression after taking the Laplace transform. We will get this thing I of t. You just verify yourself, and I will provide the study material for this topic. V naught divided by capital L, okay, into P1 minus P2 into you can write e to the power P1t minus e to the power P2t, and you just write the expression of P1t P2t in terms of RLC. Okay, so you will get ultimate this expression. So this is the response of the second order circuit, consists of resistance, capacitance and inductance. Okay, so L V naught by L into P1 minus P2 into e to the power P1t minus e to the power P2t. Okay, any doubt? Okay, thank you everyone. In next class we will discuss about resonant circuit. So you just read about the resonant circuit, series resonant circuit. In next class we will discuss about series resonant circuit. So Laplace transform, this topic, this is the last class. If you have any doubt, anyone, regarding the Laplace transform or impulse response, step response, singularity function, properties of Laplace transform, initial value, final value, etc., you can ask me or you can write in your chat box. One thing before closing this class, let me tell you just one thing. You calculate the Laplace transform of a periodic function. In next class, I will check how many students solve the problem Laplace transform of a periodic function. Let me write here. In next class, you will show me the Laplace transform of a periodic function. Calculate the Laplace transform of a periodic function. You know what is periodic function? Periodic function is nothing but a function which repeats itself after a certain interval. Periodic function means f of t equal to f of t plus t, sorry, f of t plus n capital T, where capital T is the period of the signal and n is the integer, where capital T is the period of the signal or function, and t here t greater than 0 and t greater than 0. If t less than 0, then it will be, instead of plus you need to use plus minus sign. So you just consider t greater than 0. If less than 0, you need to write plus minus sign. So n equal to here, n equal to 0, 0, 1, 2, 3 and up to n. Okay, infinite I mean. Your task is to, this is one problem, everyone solve it yourself. Okay, calculate the Laplace transform of a periodic function. Calculate the Laplace transform of a periodic function. Okay, any doubt? Thank you everyone. We will discuss resonant circuit in next class. So you read about this circuit, resonant circuit, series resonant circuit. So thank you. Okay.